Hello everyone, and welcome to Chapter 5, Chemical Quantities and Reactions. Our first section is going to cover the mole concept, and the mole is a central concept for chemistry, and so it's very important that you get this, and so make sure that you pay special attention to this section. A counting term states that there are a specific number of items, and the example here, as you see, if we call 12 eggs a dozen eggs, you still know that that means that there are 12 eggs. A case of Cokes is 24 cans of Cokes. So those are what we call equalities, okay? That we know that if we only have one case of Cokes, that means that we have only 24 cans. A ream of paper, the other example, that means that there's 500 sheets of paper. And so a gross is 12 times 12, or 144 of an item. So these things are equalities because I can state that amount, that counting unit, either way. And depending on who I'm talking to, you should know that those are equivalent, or why we call them equalities. Small things such as atoms and molecules and ions, we use the mole to say how many those are, and you'll see why. 1 mole of anything is 6.02 times 10 to the 23rd of whatever that item is. This is called Avogadro's number, not avocado now, but Avogadro's number, 6.02 times 10 to the 23rd. And as you can see here, that's a really big number, isn't it? Okay, so we can put that in scientific notation, or we can just say 1 mole of something is 6.02 times 10 to the 23rd. And then if you're in chemistry, you know that that's what that means. So it's an equivalent. So if you have 1 mole of a particular element, you have 6.02 times 10 to the 23rd atoms of that element. So for example, carbon, if you have 1 mole of carbon, you have 6.02 times 10 to the 23rd atoms of carbon. 1 mole of sodium, you have the same number of atoms of sodium, 6.02 times 10 to the 23rd. And I tell my classes that, you know, if I had 1 mole of elephants, then I would have 6.02 times 10 to the 23rd elephants. So anytime I say I have a mole of something, that means exactly the same thing as saying that I have 6.02 times 10 to the 23rd of that item. So if I have a mole of an element, 1 mole of aluminum, for example, like I have here on this particular example, okay, and that means I have 6.02 times 10 to the 23rd atoms of aluminum. Same thing with sulfur. If I have 1 mole of water, that's not an element, that's a molecule. So I have 6.02 times 10 to the 23rd molecules of water. Or I could have a mole of vitamin C, or I could have a mole of sodium chloride. But if it's a molecule, then I have 6.02 times 10 to the 23rd molecules. If it's an ionic complex, okay, then it's proper to say 6.02 times 10 to the 23rd formula units of sodium chloride. So when we use Avogadro's number, we use that as an equality. And since it's an equality, remember, I can write that as a conversion factor, so that I have 6.02 times 10 to the 23rd particles over 1 mole, or I can write it 1 mole over 6.02 times 10 to the 23rd particles. What this will allow me to do is, by knowing how many moles I have, I can tell you how many atoms or molecules or particles of something that I have. So when we calculate atoms or molecules, we state the quantity that we need. We write the plan to convert moles to atoms or molecules using Avogadro's number. We're going to use Avogadro's number to write the conversion factor, and then we're just going to do the calculations. So in this particular example, it says how many CO2, carbon dioxide molecules, are in 0.5 moles of CO2. Well, we know that there are 6.02 times 10 to the 23rd molecules in 0.5 moles, in 1 mole of CO2. So how many would be in a half a mole of CO2? So you're given 0.5 moles of CO2 and you're wanting to find out how many molecules there are. So you know you're going to use Avogadro's number to go from moles to molecules. And so you figure out which one of these that you're going to have to use. Since you're given moles first, you know that moles will have to be on the bottom of your conversion. And so the 6.02 times 10 to the 23rd will be on top. And so that's 3.01 times 10 to the 23rd molecules of CO2. If you look in, I've got some EduCreations videos out there that go in, I believe, a little more depth into how that you use your calculator and entering that into it so that you get this exponent correctly. But whatever calculator you're using, put that in there, multiply it by this number, and make sure that you're getting this, okay? Now on this one it's pretty simple because you know it's half of whatever that number is. But if it's like 12 or something like that moles, then you're going to have to be able to move this exponent, and so it's a lot better if you can do that with your calculator. So let's do a learning check, and like I said, you can always put me on hold and go through this yourself and make sure that you understand everything. All right, the number of atoms in 2 moles of aluminum atoms is, okay, and you can do mental math on this probably, but the way you set this up is 2 moles of aluminum times the conversion factor. We know moles is going to go down here because we have to cancel out moles. Okay, so we know 1 mole, and that's 6.02 times 10 to the 23rd atoms. And then moles cancel. Should say aluminum. Okay, and so that should give us, put that in your calculator, 1.2 times 10 to the 24 atoms of aluminum. Okay, and so I guess that would be answer C. And again, as always in these learning checks, the solutions in your learning check handout will give you all of these more detailed step-by-step solutions than from what I did. But we got the same answer, so all is good, right? The number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur. Now this time it's turned it around. This time what we're given is 1.8 times 10 to the 24 atoms of sulfur. So we write that first, 1.8 times 10 to the 24 sulfur atoms. So since we're given sulfur atoms this time, what do we know goes on the bottom? Yes, sulfur atoms. And it's asking for moles, so we're good to go on that. So we know that 1 mole of sulfur gives us what? What's the magic number? 6.02 times 10 to the 23rd sulfur atoms. And then when we multiply that out, what will that give us? All right, my calculator told me it was 2.99 moles, so I'd say that that's close enough to 3, wouldn't you? So 3 moles of sulfur. Hopefully you got the same thing. You can always remember, go through these more complicated instructions, but we get that same answer. Okay. So sometimes what we're more interested in, instead of how many molecules there are in a certain number of moles, we might want to know, like, how many carbon molecules are there in a formula. And so in this particular formula, you see they're showing you that there's 9 carbons, there's 8 hydrogens, and there's 4 oxygens in 1 molecule of aspirin. And so we're going to see that we can actually use that ratio to work problems to our advantage. So in a formula, the subscript shows how many of each of these types of atoms is in that particular compound, and this is saying that there are this many. There are 9 moles of carbon in 1 mole of aspirin. There are 8 moles of hydrogen, and there are 4 moles of oxygen in 1 molecule of aspirin. And so that gives us a whole slew of conversion factors. That there are 9 moles of carbon in each mole of aspirin, 8 moles of hydrogen, and 4 moles of oxygen in each mole of aspirin. And then of course you can always flip those over, because we can use those as conversion factors because those are equalities. So our first learning check to apply that, we're using aspirin, the C9H8O4, and it says how many atoms of oxygen are there in 0.150 moles of aspirin, whose formula is C9H8O4. All right. Put me on pause if you want and see if you can work this or not, and then come back and we'll work it together. Okay, so what we are given is 0.15 mole of aspirin. Okay, so I've got 0.150 moles of C9H8O4. All right, and that's what I start with. All right, I know that what's going to come next is going to have moles of C9H8O4 on the bottom. How do I know that? Well, because I have to cancel that as I'm going, right? So what is the molar relationship between oxygen and aspirin? Well, for every 1 mole of aspirin, if you recall from that slide before, there are how many oxygen moles? 4. Okay, so for every 1 mole of aspirin, there are 4 moles of oxygen. So 0.150 moles times this conversion allows me to cancel out moles of aspirin, and that's going to leave me with moles of oxygen. And so if you multiply 0.15 times 4, that should give you 0.6 moles of oxygen. Here's your detailed steps. Oh, one thing that I didn't do is read. Instead of just moles of oxygen, it wants to know molecules. So once I get to molecules, what I can do is I can say 0.6 moles of oxygen times my old buddy, what? Avogadro's number. I know that mole of oxygen goes on the bottom, and I could have done this all in one long problem, or I can break it out like this in steps. I know that Avogadro's 6.02 times 10 to the 23rd atoms of oxygen, and then I cancel moles, and then 0.6 times 6.02 times 10 to the 23rd should give me, if I did that correctly, 3.61 times 10 to the 23rd oxygen atoms. All right, let's see if we did it right. Yep, we did. All right. So yeah, let that be a lesson to you. Even the teacher doesn't read as closely as she should sometimes, and so make sure that you read so that you know exactly what you're looking for when you get done with the problem. And that's the end of section 5.1 and our introduction to the concept of the mole. And so hopefully you are doing some of your mastering chemistry and doing some extra problems on those. I also have some worksheets for you to use to give you some extra practice that have the answers at the end, so look at those. I also have an EduCreations video on the molar concept and work some problems that are in addition to this, so feel free to look at those as well. You'll find those under Unit 3 on your Blackboard.